So it was found from the first sizing of the heat exchanger that we need a very long tube in order to have a very large surface of heat transfer between the flue gas and the water that we want to heat, to recover heat from the flue gas. In order to improve this heat exchanger, it was identified that it's the hot side, so the gas side of the convective heat transfer that is causing problems, because the heat transfer is not effective enough on this side. So in this part we try to enhance this outer surface by adding fins. The fact, I mean, adding fins will augment the heat transfer area between the solid, so between the pipe and the gas that will exchange heat with it. And so by enhancing this surface, we want to improve the effectiveness of this surface and to reduce the thermal resistance of the outer convective heat transfer. So, first thing we want to look at is what is the fin efficiency. So, the fin geometry is proposed in the exercise sheet, and we also have one chart in order to find what is the fin efficiency. Before going further, I just would like to make sure you know exactly what does the fin efficiency mean. The fin efficiency is the ratio between the actual heat transfer we have from this fin divided by the maximum heat transfer we could have with this fin geometry. So if I reformulate this, we divide with the heat flux we would get if we had this fin geometry with a material with infinite thermal conductivity. If I tell it once again in other words, it's the heat transfer we would get if the whole surface area from the fin was at the same temperature than the base of the fin. And this is not the case, because in reality we have conduction across the fin that will decrease the temperature of the fin. So at the tip of the fin we don't have the same temperature than at the base. But here we have at denominator the maximum heat transfer if the fin was totally at the same temperature than the base. So that's the definition of the fin efficiency. So in order to find it, you have a chart with two parameters that you need to define first, and once you know them, you can find the fin efficiency for exactly the same geometry that we have in our example or in our exercise. So you have this first parameters that you need to calculate, and also the second one. Just be careful with one thing. The nomenclature, so the name of the different variables, is specific to this chart, and here in particular there are some parameters that that have the same name than that other variable that we have been using in this exercise. For example, L has another meaning here, so be careful to use the meaning of the chart when you do this calculation. And maybe one more thing is this parameter, maybe you recognize this one, it's called the module of the fin, and if you have done some fin design before, you probably recognize this one. So once you have calculated both parameters, then it's just about reading on the chart, and you find the fin efficiency. I read 0.82, and that's a really good fin efficiency, and this is due to the fact that we have a design with very massive fins, so it's improving conduction across the fin.